But what's this? Now we're not talking about sign, we're talking about size. And the power of size is a curious thing. Make some man weep, make another man sing. Don't think too hard about those lyrics. All right, moving on. So let's change the size from an unsigned long to an int, an integer, a 32-bit value instead of a 64-bit value. What are the effects going to be on the code? So here's our new code with ints instead of longs, and we get the following. SLLW, SIRLW, SIRAW. What's the difference with those shifts? Well, the SILW is shift left logical as usual, but now it is a shift by register with a word size register. So the W suffix, like we had seen before for add W and sub W, is used when RV64I code wants to use word sized registers, the 32-bit registers, instead of the full 64-bit register size. Now, of course, the reason why this came up was because we were using ints, not longs, 32-bit values. So SILW is just going to be like we've seen before. We have a source register, a source2, and now because we specifically are using word sizes, there's no longer a question of is it shifting by the bottom 5 bits or the bottom 6 bits based on whether you're doing 32 or 64-bit. It's always treating it as a word size register, so it's always the bottom 5 bits of RS2 are interpreted as the number of bits to shift. So we've got the source and destination, and like I want to emphasize, and the destination is going to be treated as a word sized register, and it's ultimately going to do the math as if they were word sized and then sign extend the results to 64 bits. So let's look at a concrete example. We've got SLLW, T0, T1, T2. The bottom 5 bits are set to C for a 12-bit shift. And now we're going to use the constant value 112233 all the way up to 88. And now we are going to take T1, treat it as a word size register. So lop it in half, only focus on the 55667788, and shift that over by 12 bits. So 12-bit shift to the left means that we're going to take this stuff at the bottom, move it 12 bits to the left, and then ultimately, based on whatever our most significant bit is, that will be sign extended into the upper 32 bits. So treat it like it was a 32-bit register, which would have yielded 6, 7, 7, 8, 8, and then 3 zeros, but then sign extend whatever the most significant bits are to yield a final 64-bit result. Let's see a different example of that. We've got now D, we're going to shift by 13 bits instead of 12 bits. And so if we once again have 112233 up to 88, and we shift that left logical by 13 bits, that is going to mean that that most significant bit, which was previously 0, now it's 1 over, and so this thing that was 6, which was 0, 1, 1, 0 for 6, got shifted over 1 more, and now the most significant bit is 1, and so we've got all Fs followed by CEF1 and 4 zeros. So that's the way that this shift left logical with word size works. Treat it like it's 32-bit, but then when you're done, extend it up to a 64-bit value. Then let's look at the shift right logical, and of course it's going to be all the same sort of ideas. Shifting right logical, so you always fill in with zeros, and word size registers. Source and destination word size, 0 extend the result to 64 bits. You could say that we're sign extending it, except because this is a logical right shift, the upper bits are always going to be zeros, so I'm just going to say 0 extend. Okay, set it up, shift by 12 bits. Here we go. We've got 11232233 and so forth. But again, we're going to treat it like it's a bottom 32 bits, and we're going to shift that right by 12 bits. And so that goes right by 12 bits. And then we are doing a logical shift, so we don't even care what the most significant bit was. We just always fill it in with zeros. And so that yields hexadecimal 000556667. And like I said, it's 0 extension or sign extension if you want, but either ways, it's always going to be zeros because a logical right shift always fills the most significant bits with 0. And finally, we have SRAW. Same thing, shift right, but now it's arithmetic, word size, 5 bits interpreted, this second source register interpreted as 5 bits, source and destination word size register, sign extend up to 64 bits. Let's just see an example. An arithmetic shift, of course, as usual, is going to take the most significant bit, which in this context, because we're using a word size register, it's the bit 31 of the word size register that is our RS1 interpreted. So we take that most significant bit of we take bit 31 essentially of RS1, and we use that for the filling in of the shifted bits. So we're going to assume a 12-bit shift again. We've got 1, 1, 2, 2, 3, 3. I chose to put an A in here instead of the 5 because I want that most significant bit to be a 1, so that I can show you that when we shift over, yes, they go over by 12 bits, but then we take that 1, and it's an arithmetic shift. We fill in all of the ones up here, and then above and beyond that, we sign extend the result to 64 bits, yielding all Fs A5667. Had we left our 4455, that 5 would have had a most significant bit of 0, and that would have been filled in instead. Okay, well, that is just another permutation on the shifting. We've got shift right, shift left, arithmetic and logical for right, no arithmetic for left because it's going to be just the same thing. So go ahead and step through the assembly and make sure you understand what's going on. To double check things, you can of course provide your own values in the command line arguments and see the different values that result so that you can confirm it behaves the way you expect.